Problem sheet 7, question 2. You have 8 cardboard boxes in your house with the following dimensions. So we have 8 cardboard boxes, each have a label, a Greek letter, a length, a width and a height. They are fragile and cannot be rotated or flipped. A box can be stacked on top of another box if its length is shorter and its width is shorter than the other box. Use dynamic programming to find the tallest possible stack of boxes. So with dynamic programming, the first thing we have to do is formulate this problem as a problem on a graph. And a taller stack of boxes can correspond to a longest path problem. But let's set up our graph in such a way that that's true. So on our graph, we will let boxes be nodes and we'll let edges be relations whether a box can be stacked on top of another. So for example, if we have box A and box B, and there's an edge from A to B, then A can be stacked on top of B. That means that the length of A is shorter than the length of B, and the width of A is shorter than the width of B. Now we can see that this would be a graph, and it would be a directed graph as these edges have a direction. Would this graph be acyclic? Well, we'll have to consider this relation carefully. All of A's descendants will be all of the boxes that A can be on top of in the stack. So either A is directly stacked on top of another box, or it's indirectly stacked. There's a few boxes in between. Now that would mean that A has a shorter width and a shorter length than all of its descendants. How would a cycle occur? A cycle would occur, for example, if there was a way of connecting A back to itself. That would mean that A is a descendant of itself, and we just said that all of A's descendants have a shorter length and a shorter width than A, but A cannot have a shorter length and a shorter width than itself, so this would be impossible under this formulation. Now drawing this directed acyclic graph will be quite complicated. There's going to be a lot of edges. So all we really need is key information about this graph. We don't really need to draw it because it'll be a mess. The key information we'll need is the list of edges. We'll want to know what node this edge leaves, what node this edge enters, and the length of that edge. Now for an edge from A to B, that would correspond to stacking A on top of B. That would increase the stack by the height of A. And so the length of that edge will be the height of the node it is leaving. It would also be useful to introduce an extra node star which represents the tabletop, and in that case the longest path from any box to the tabletop will represent the tallest stack of boxes that we can create. Having introduced that extra tabletop node, we can immediately write down 8 edges because any box can be stacked on top of the tabletop. Now we will go one by one through the boxes, listing all the possible boxes that can be stacked on top of it. So first consider alpha. The boxes that can be stacked on top of alpha are gamma, delta, epsilon, and eta. All the others have a length or width equal or greater than alphas. Now consider beta. The boxes that can be stacked on top of beta are gamma, delta, zeta, and eta. Now consider gamma. There is no other box that can be stacked on top of gamma. Delta, the boxes that can be stacked on top of delta are just gamma. Consider epsilon, the boxes that can be stacked on top of epsilon are gamma, delta and eta. What boxes can be stacked on top of zeta? Gamma and eta. Now consider eta. No box can be stacked on top of eta, as there is no other box with a smaller width than 3. And theta, the boxes that can be stacked on top of theta are gamma and delta. We would now like to order the edges so that all the nodes preceding a node are descendants of the current node. That can be quite complicated to figure out without visualizing the graph, but in this case we have this is just one possible ordering. Let us check. We've put the tabletop first. This tabletop has no descendants, and so we can analyze all edges that go into the tabletop. Then we've put alpha. Out of the non-highlighted edges, the ones we haven't analysed at this point in the sequence, alpha has no descendants, and so we can analyse all edges going into alpha. Next we have beta. Out of the unhighlighted edges, beta has no descendants, and so we can analyse all edges going into beta. Then we have theta. Theta has no descendants, so we can analyse these. Epsilon, we could analyse these. Delta, we could analyse this. Zeta, this. And finally, we can just analyse gamma and eta then. We are now ready to begin the value iteration algorithm. As we are looking for a longest path, we care about the current node that we are leaving from. Where do we go in to next? What is the reward for following that path? What would the resulting stack be if that path was in our longest path? And finally, therefore, what is the value of that box? What is the largest stack we can create from that box downwards? We'll begin with the tabletop, which goes nowhere and therefore wins no reward and has a value of 0. A tabletop has no height. We'll then consider alpha. The only place we can go is the tabletop. The extra height we will add to the stack if we place alpha on the tabletop is 10, the height of alpha. And so, if that path was in our longest path, the longest path from alpha will have height 10. We can then analyse beta. The only place we can put beta is on top of the tabletop, resulting in an extra height of 6, the height of beta. And so beta has value 6. Now let's consider theta. The only place we can place theta is on the tabletop, the height of 6. And so theta has a value of 6. Next we will consider epsilon. Epsilon we can place on the tabletop. We can also place epsilon on alpha. Either way, epsilon will contribute a height 11 to the stack. If we place epsilon on the tabletop, the height of the stack would be 11. If we place epsilon on top of alpha, the height of the best stack from then on would be 21. And so the value of epsilon is the best from there on, which is 21. Next we will consider delta. We can place delta on the tabletop. We can place delta on top of alpha, on top of beta, on top of epsilon, and on top of theta. Either way, the height of delta is 7. And each of these actions, placing delta on top of each of these stacks, will result in the best height possible there is placing delta on top of epsilon, the height of 28. We will now consider zeta. We can place zeta on the tabletop. We can place zeta on top of beta. Zeta has a height of 4. If If we were to place it on the tabletop, the stack would be height 4. If we were to place it on beta, the stack would be of height 10. And so the best we can do with zeta is a height of 10. We'll now look at gamma. We can place gamma on the tabletop, on alpha, on beta, on delta, on epsilon, on zeta, and on theta. Each time, gamma would contribute a height of 3. And the resulting height from each of these would be and the best height we can do there is by placing gamma on top of delta to get a height of 31. Finally, we will consider eta. We can place eta on the tabletop, on top of alpha, on top of beta, on top of epsilon, or on top of zeta, each time contributing a height of 4. The resulting stacks then would be and the best height we can make with eta on top will be of height 4 plus 21, which is of height 25. The final thing to do is to read off the solution, and so of all the nodes, the one with the greatest value, so the one with the greatest stack height, if that's the box on top, is gamma with a height of 31. How did we get that? We got that by stacking gamma on top of delta. For delta has a value of 28. How did we get that? We stacked delta on top of epsilon. How do we get that? We stacked epsilon on top of alpha. And how do we get that? We stack alpha on top of the tabletop. Therefore, our solution is to stack first place alpha on the tabletop, then stack epsilon on top of that, then delta on top of that, and then gamma on top of that, giving an overall tallest stack height of 31.